Okay, so for the lab, today's lab is on supervector machine. We start with the linear model, and we will make some slight modification to the models that will allow us to actually be able to train the model without having to introduce new tools. We have seen the primal formulation, and we have seen that the primal formulation can be solved through the dual expression. We will solve the dual formulation also for the linear model, because then we will not have to write the code twice and have it differently for the non-linear and for the linear classifier. So for this reason, even if it's not the best approach, we will use the dual solution, the dual problem already. There are other reasons to use the dual problem rather than the primal for our task. Solving the primal loss is non-differentiable, so the BFGS algorithm may have issues finding a proper minimum of the objective. It will typically work, but with respect to logistic regression, we can't guarantee that we will reach the minimum. The model is not guaranteed to work always. While for the dual, it's convex, so we don't, and it's differentiable, so we don't have issues. The problem that we have is, if we want to use BFGS with the dual, is that we have constraints to satisfy. The version of BFGS that we used is able to handle what are called both constraints, that is, constraints of the type a variable is between some value A and some value B, and this holds for all variables. So for all variables, I can define bounds for that variable. But the constraint that we have in the dual problem, the sum of the alpha z I equal to 0, is not a box constraint. It cannot be expressed in this way. So this is a constraint that we can't use with our current BFGS implementation. And this is actually a problem for us. We'll see how to deal with that in a moment. Now, here you have all the explanation of how you would solve the standard SVM model. You would compute the H matrix starting from the dot products between the different samples. Then we have the relationship between W and H that we remember that we have defined in class. So we would solve the problem in terms of alpha, then we could recover the optimal solution for W. In class, we didn't say how to recover the optimal solution for B, but to compute B, we just need to take one sample that is a supervector on the margin, for which this must be equal to 1, and then once we know W, we know Z, we know Xi, the only unknown here is B. So we could solve for B. Which are the supervectors that are exactly on the margin? What is the value of alpha that tells us that the supervector is on the margin? If it's greater than 0 and smaller than C, then it's a supervector on the margin. So we will need to look for those supervectors. And then, as we said, we could implement scoring for the primal either by recomputing W or by computing the kernels. This is what we will do, because for the nonlinear we will have only this last option between the training samples, the training supervectors, and the samples that we need to score. Now, as we said, for linear we could use both the primal and dual, but for the nonlinear we would just need to use the dual. So we will use the dual also for the linear to avoid doing things twice. Then we said another reason for choosing the dual is that BFGS could converge if we didn't have the constraint, the sum constraint. Now, this constraint derives from what? Derives from the fact that we needed the Lagrangian derivative with respect to the bias term to be equal to 0. And that resulted in this constraint appearing. So what we will do now is we will modify our SVM model in a way that this constraint does not appear anymore. This is not exactly the original SVM model. It's a modified model that may behave worse than the original one, but it's easier to optimize. So we trade off being rigorous in the mathematical formulation of our problem with easiness in being able to find a solution that works for the modified problem. How? Essentially, we define a new problem without an explicit bias. However, since the bias is important, we define a new model that does not have an explicit bias, but has an implicit way of representing the bias. How? Well, this is the expression of an SVM that does not contain the bias. But if rather than training with our original samples xi, we train with an expanded version of xi that contains the original xi and then a value 1, then we can observe that the score between the expanded features and the vector w hat would be what? Well, let's say that w hat contains components w, and the last we call it b, the last component of this vector w, we call it b, so these are d components, and this is 1. xi is in r to the power d, so xi hat contains xi 1, so d components and 1 component. This is what? It's w transpose xi plus b. So this looks pretty much like an hyperplane plus a bias. The difference is that here we are taking the square norm of w hat, but the square norm of w hat is the square norm of w plus b squared. So essentially, if we apply this model where we replace our samples with these expanded samples, we train a model without the bias terms with this expansion, we are simulating a model which has a bias term, but we are also regularizing the bias. This is the difference with the original SVM. In the original SVM, we are not regularizing the bias. And indeed, we should not regularize the bias, because the bias, the norm of the bias is not related to the margin of the classification margin. So introducing a penalty on the bias, it means that, for example, if our data set is far from the origin, then the SVM will have trouble in finding a good solution, because remember that the bias is related to where W transpose X plus B is equal to 0. So W transpose X equal to minus B defines where this plane lies. If I force B to be close to 0, then my planes may not move very far from the origin, because they would be penalized. So if I introduce this process, for example, then it becomes important that my data is at least somehow centered, so that the actual bias that the bias that I estimate is small, but is sufficiently large that it can properly model where I should put my separation rule. However, so this is an issue. This issue can be also mitigated, but okay, we'll see how a possible way to mitigate it that actually makes training slower but reduces the impact of this phenomenon. The benefit is that, okay, let's see first the mitigation. So this is how we would extend the model. If rather than using 1 here, we use a large value k, then essentially that means that we are effectively reducing the regularization effect on the bias. Why? Because now my transformation, W transpose X hat, the model in the hat space will be W transpose X plus BK. So you see that if K is large, to obtain a reasonable bias, I can do it with a smaller value of B. So the larger I make K, the lower the bias that I need to obtain a same score, which means that I can afford larger values of B because, well, I can afford large values of B times K with a small b. A small b is allowed by my model because my model is penalizing large values of B. If a value of B is small, it's not being penalized much. The problem is that if I put here a large value of K, then the method that we will use for training will become slower typically. So it will take more time to find a good solution, the larger, the optimal solution, the larger the value of K. So we can mitigate the problem, but we will pay for that in increased training time. So we will just use K equal to 1 in the following. With this expansion, if we rewrite the the model, we will see that the constraint sum of alpha I z I equal to 0 disappears because we don't have the term b explicitly anymore. So if we write it as a function of w, then w hat behaves like a standard vector w. So the only thing that we need to remember is the relationship would change w hat equals sum of alpha I z I xi hat. That's the relationship, but we don't have the constraint on the sum of the alphas anymore, which means that the equivalent dual problem is a dual problem where H has changed because now I need to compute the kernels between the expanded features. And notice that if I had x1 hat transpose x2 hat is equal to x1 transpose x2 plus k to the square. If a k is equal to 1, it's plus 1. So I can compute it from the original dot product, adding 1. I will need to use the expanded features dot products, and then I can train the model with the expanded features. So the idea here is we will train this new model that behaves similarly to an SVM if our data set is not far from the center and if the optimal SVM didn't require a large bias, by simply, well, one possible way if we use linear functions is to simply expand our features by adding a 1 and training a model that optimizes this objective without the 1. Notice that a second alternative that then will be a necessity for kernels is, rather than doing explicitly this expansion, we compute the matrix H by computing the terms zi, zh, xi hat, xj hat, xi transpose, xj hat transpose. We can first compute the term xi, transpose xj, and then add 1 to those terms. Each of these will correspond to one of these entries. Two possibilities. In the laboratory, it says to extend the feature vectors, but then in the nonlinear model, we will use this other alternative. So choose which one you prefer here. Then our optimizer is an optimizer that finds the minimum of a function, but here we need to maximize the dual. So how do we maximize the dual? We maximize the dual by minimizing minus the dual. So we minimize a loss function L that is minus the dual objective function. We need the gradient, and now we need the gradient because it will take typically many more iterations than the logistic regression model. The gradient can be computed in this way. So you already have the gradient expression there. It's fairly simple to implement the gradient. Actually, you need the gradient is a subpart of the objective function itself. So this you need to compute also for the objective function. So once you have it, it's easy to compute the gradient. Now, how do we specify our box constraints? We need to pass the boundaries of the alpha to the optimization function. The optimization function can receive a list of tuples. Each element of this list refers to one optimization variable in the same order as they are passed in the vector that we pass to the objective function. This tuple contains the limit, lower and upper bound of the corresponding variable. Since for all variables the limits are 0 and c, we just need to create a list that contains the tuple 0, c, a number of times equal to the number of samples. The number of alpha i's is equal to the number of samples. Then you can extract the primal solution in this way, and then you can use the primal solution directly to compute the score. In this case, pay attention that the primal solution is the extended W. So to compute the score, either you compute the extended test vector, or from W hat you extract W and B, and then you compute explicitly with the original test vector the score. Then here we will use a threshold 0, as we said in class. Since we don't have probabilistic interpretation, it doesn't make sense for the moment to try different thresholds because they would not make much sense anymore, anyhow way. So we will see how to address this later. Again, during the laboratory, you will need to select C, so cross-validation. Here you have values for different Cs. Now, to see whether your solution is correct, you can compute the duality gap. And here it's fairly important because with the SVM and with the solvers that we use, which are not optimized specifically for SVM, you may end up with solutions that are not exactly what you have in the laboratory text. So it's important that you are able to compute the numerical, duality gap, because from the duality gap you can see whether your solution is not exactly the same but good, or not exactly the same but bad. To compute the duality gap, you need to compute also the primal objective. So you need to implement also the primal objective. Then the difference between the primal and the dual, or if you use minus the dual, that is the function we implemented for BFGS, the sum of the two will be the duality gap. Then pay attention that we need to change some of the parameters that control the convergence of the BFGS algorithm, because the standard one typically are not enough to ensure that we reach a good solution. And if you don't reach a good duality gap, you may also need to check whether your method stopped because it reached the limit number of functions or the limit number of iterations, and if needed, try to increase these values as well. Here you have a table with the results on the IRIS dataset. Now, as we said, you may not obtain exactly this number. The important thing is that the duality gap is few orders of magnitude lower than the objective function. If it's not, then you probably have some issue in your convergence. If it is, then your solution is probably good. Well, no, it's good, without probably. You may even have a duality gap that is negative. Now, duality gap that is negative mathematically is not possible because the primal is always larger or equal than the dual. So why can it happen? Because the way you compute the primal and the dual is different. Different numerical errors in the computations may lead you to an error in which you underestimate the primal or you overestimate the dual. So the dual may appear larger than the primal. This is acceptable. It is acceptable if the order is in the order of magnitude of the machine error. If it is, then it's probably a numerical error. If you get a duality gap that is 1 minus 1 to the power minus 7, this is too large compared to machine precision. There is something wrong, probably in your computations. Of course, if you get minus 100, then there is something very wrong in your computations. This is what you should obtain. You also have minimum and actual cost computed for an application with prior pi-t equals 0.5, so threshold equal to 0, and you can check how that you obtain the same values. Now here they are typically quite not very good. For example, here you can see that there is a model which has 0 min DCF, which means that whatever threshold 0 min DCF means that I have no errors on the validation set, which means that a well-calibrated model will also have no error on the validation set itself. But here you see that if I select well the threshold, I don't have any error. If I use the standard threshold, which in case is even the SVM threshold itself, because the threshold is exactly 0, then I may make many more errors than what I could with a better threshold. Again, this we will see next week. Then we can move to the kernel version of the SVM. This time, we need to replace H with the function that computes the kernel. So we need to compute the elements of H calling the kernel function rather than computing the dot products. Now, first problem, how can we compute the duality gap with the dual, since we don't want to compute the explicit expansion of the feature vectors? Luckily, we can express also the primal function, the primal solution, as a function of alpha. Remember that W is equal to this, So whenever we have w hat like this, if now here we have some phi of x, and here it's a w that depends on, let's call it w phi for the expanded features, whenever we had w transpose xi, we can replace w with this expression. And then the resulting expression of the primal written as a function of alpha would look like this. So if I know alpha, I can also compute the equivalent primal solution. And that allows me to compute the duality gap. Now, this needs to be implemented as well, because otherwise we can't check whether the duality gap is small. Then, in the dual formulation, the score must be computed through kernel calls. So we need also to implement correctly the function that computes the score. You can try different kernels. Pay attention that in this case, the simulation of the bias is not implemented through an expansion of xi, so we will not do this expansion, but we will compute the original kernel and then add a constant. Why? Because that's the equivalent of what we were doing from kernel level. We said when we were doing this expansion, what did that mean? That the dot product was the original dot product plus 1. It's the same for all kernels. You shouldn't compute the kernel with the expanded features. You need to simulate the bias. So you should have the original dot product plus 1, because what you want to compute is the original expanded features and with a 1 added at the end. When you want to, your hat vectors in this case would be the original expanded features and a 1. So the dot product would be the dot product between the original expanded features plus 1. It will not be the expansion of the original features with an additional 1. So the correct way of doing it is taking the original kernel, compute the standard kernel matrix, so all the kernels, but rather than using directly the original kernel, you add a constant to the final expression. The constant, again, in the table, you have different values, 0 and 1. For the laboratory, we'll essentially use 1. When the value is 0, it's as if I was not using the bias term at all. When the value is large, it's as if I was using an SVM where the bias is not regularized. You can imagine that if this constant is large, all the values in the kernel matrix become much more closer between them, because if this value is large, then the kernel matrix becomes sort of flatter. All the values become much more similar. And this is the reason why LBFES will have more trouble finding a solution. When H contains values that are much more similar among them, the number of iterations that I need to find a solution is typically larger than if I have a kernel matrix that is nicely diagonal. So that means that it will take more time the larger the value of this constant. For this reason, we will just use a value of 1. Here you have again the same table with loss, primal, dual, and duality gap. Then for the project, what will you be asked to do for the project? Well, for the project, we need to train the SVM. Now, you will see that training the SVM is more typically slower than the other models, so the suggestion is prepare your code well for the project using a subset of the samples to debug the code, and then train the real models only once you have finished debugging the code, because if you try to do debugging of the code using the full dataset, it will take much longer. Then once you have prepared your models, what you are asked to do is try starting with the linear model. Again, fixing k equal to 1 to avoid tuning also that value. Also tuning that value may be useful. Use C as a hyperparameter. Similarly to logistic regression, we will use a log-spaced set of values that we will try for C to select the optimal ones. Use mean and actor DCF for the target application using a logarithmic scale over C, the same as we did for logistic regression, nothing new. The two models we said are very similar. Just remember that in logistic regression, large value of lambda is large regularization. Here, small values of C is large regularization, while large value of C means lower amount of regularization. C multiplies the loss term in the SVM. And check what happens. Is regularization important here? Does it help? Does it not? Do we need to regularize a lot or not? Are scores well calibrated? How does it perform with respect to other linear models? We said it's important to center. In this case, it's important because we have the bias problem. So try to also recenter the data. Would it change the results? Of course, we will need to try also other preprocessing. We will not. But in this case, it's worth trying centering because we said the way we regularize the bias has an effect if the data is not centered that is much more visible than with other models. So it may or may not, you will have to discover, affect the results. Then we consider the polynomial kernels. We start with degree 2. We will see in the polynomial kernel we'll actually use a more general expression than in class, where the value that we have here is a constant C that we could also tune, but we will not. So we use just C equal to 1. But this is just to say that we may want to tune that as well. Again, for timing reasons, we will not. But it's something we could do to obtain better results. And then try without the bias term. Why? Because when we have C equal to 1, we have X transpose, the kernel is this. If you develop this, you will see that there is already a +1 at the end of the kernel in any case, because this will be x1 transpose x2 to the square, plus 2 times x1 transpose x2, plus 1. So there is already a term that behaves like the bias term. So there's no need to actually add an additional value for the bias. So here in this case, you can use the term equals to 0. And then, in this case, you can just use the original non-centered features. You are not asked to center them, but if you want, you can try. Try the model with quadratic models, with quadratic kernel, and see again mean and actual DCF, what happens with quadratic model, how this compares with the previous quadratic models, so gist regression and Gaussian, in terms of mean DCF and also in terms of act DCF. Are these well calibrated or not? Are they better or not than the other models? Then, finally, we do the same with the RBF kernel. In this case, the RBF does not contain a term that behaves like the term that we use to simulate the bias, so we will need to add the key term in the kernel. We use just one. And then now we have two values to optimize, the kernel gamma and the SVM C. Try a grid search. Here you are already given reasonable values for the grid search. Notice that the C values here are different from the C values that we used for the linear and quadratic model. Why? Because we did for you a pre-selection of reasonably good values so that you don't have to search the whole set of possible values. And in this range, if I were using the same range, it would just be a waste for the linear models. And if I were using the range I've already tuned so that you don't have models that take too long, the larger C, the longer it will see it will take to train the model because it will try to minimize the loss. More complex decision rules, it will take more time to find an optimal solution. So we don't want C to be too large. We don't want C to be too small, so I pre-selected for you the ranges that are good for these two kernels without having you waste too much time. In this range, try to see what happens. Of course, you can try other values if you want. It's not, you are not refrained from doing that. Then see how the things change when you combine both gamma and C, so as a function of both gamma and C. And try to see what happens in terms of mean DCF and act DCF. Here the suggestion is, since the gamma values are just 4, you can do a plot where on the horizontal line you have C, and then you just plot 4 lines for the 4 gamma values so that you see everything in a single, easy to read plot. Then optional, Optional in the sense that I will not ask this as exam, but it's a good exercise to understand what's going on. Try the SVM with kernel of degree 4 and c equal to 1, and the bias term, the implicit bias term, we don't use it. You will see that the kernel with degree 4 will behave quite well. It will be close to the best that you have found. If not the best, it will close to the best. Why degree 4 works well for this dataset and works better than degree 2? You have some intuition here. The idea here is that I'm not going to tell you why, but you try to figure it out. The reasoning are similar to the ones that I was showing today in class, where I was showing why a degree 2 kernel works well for the samples that are organized in a cross-like shape. So go back to the scatter plot of your features. There is a suggestion on which to look, the last two. Figure out what a quadratic kernel would do on those features, and imagine that the degree 4 kernel is like a quadratic kernel expansion applied to a quadratic expansion. So it's like applying quadratic expansion twice. So try to figure out, when we do the quadratic expansion twice, what will happen, where the points of the different classes would end up, to see whether this is a good thing for your training set data. Okay, that's all that I had to say on this laboratory.